Hi, hope you guys are doing well. Welcome back to another edition of Bed Talks. I hope you're staying safe and being with your family or friends as much as possible. And I hope they're staying safe too. So today what we're going to talk about for this is the last section of triple integration. And we're going to be tackling a completely different type of integration technique. Because we've seen in the past that there are a lot of just different ways to look at a region when we integrate. Right? In our last couple of ones, we've done Cartesian coordinates, which is just regular x, y, and z, thinking about a height. We then saw that if we saw something on a cylinder, or if we see something in a cylinder setting, we can then maybe think about trying things in cylindrical coordinates. And now we're going to think about things if I see them on a sphere or things of that realm. So this is a reminder of kind of how we did this last time with cylindrical coordinates, right? We thought that we have this regular Cartesian coordinates, which is pretty simple, right? I have my z height, I have my y, and I have my x, right? And I get my point x, y, z, something like that. Now, the thing becomes, here at least, right, we saw then, okay, well, maybe this is not the best choice. Maybe I can think about a point, x, y, z, in a different way. Maybe I can think about this in cylindrical coordinates, maybe a point on a cylinder. So in order to do that, what we did is okay, well, I can think about a height still, but one thing I could do instead is then say, okay, well, I can give you, instead of the x and y here, I can give you the polar coordinate, right? I can do this. I can give you the polar coordinate instead of it, r and theta, and I can define this r, theta, and z. And this is a way we could do this, right? And we saw that I could do x equals r cosine of theta, and y equals r sine of theta, and z is equal to z. Great. So this is a way we could do this. Now, a lot of times we don't have cylinders. We don't have just Cartesian. Sometimes we're on a sphere, or I have a spherical wedge. What I mean by a spherical wedge is if I just have just a regular sphere and I am trying to figure out, a spherical wedge is just part of a sphere, just that little, like a little bit of a wedge kind of coming out of it. Now, why would we think about it this way? Well, think about it in terms of maybe even an astronaut. Right? If I'm, or even just a person at NASA with a telescope. So when we think about spherical coordinates, what I could do first, and this is at least what I want to think about visually first, is one thing I could tell you. If I wanted to, for instance, look at a star, if I told you, look at that star up there, in this direction here, in this direction. Well, what do I have to tell you? It's not really nice for me to think about X, Y, and Z, because I'm in thinking about sky. Cylinder, the Earth's not a cylinder yet. And one thing we might want to think about here is, okay, how can I tell a person to look up that sky at that exact point? Well, the one thing I can tell you first off about the star is how far away it is, right? I can tell you, okay, I am that far away. Okay, I'm that far away. And so if I'm here, I can go, okay, I'm that far away. I actually go specifically, okay, I'm that far away here. I'm gonna kind of make this here so we have actually, a little bit of depth here. But I tell you, I'm that far away. And then we'll call that rho. And this rho here actually is the distance away I am from the origin in a 3D sense. So for instance, if I tell you I'm 5 away from the origin, give me all the points 5 away from the origin, you would go, oh, it's just all the points that are 5 away from the origin, which is a sphere of radius 5. Something like that, center of the origin. So this is rho. That's how far I tell you. Now, again, I now have told you a full sphere of options. I need to be very specific now. I want to tell you that way. One thing I could then say is, okay, where should I move the telescope? Right, where should I move the telescope? Well, one way I can tell you is, okay, I have this angle. I have this angle, and I can kind of say, okay, well, I want to face this direction. And what is this angle actually? It's in terms of the x and y plane, right? It's actually the polar angle. It's the same polar angle as the same, like I'm moving in this direction. And it's this polar angle. It's this guy. I want to tell you where to face. Here. Okay? And based off of this, right, we can now tell you, okay, I have told you how far away I am. I have told you which direction in this horizontal plane to face. And then I now have to tell you to look up, right? And that's where the problem usually comes in for a lot of people here to think about what this means. So we call this, one thing I can tell you is, okay, imagine I start up here and I start to move my hands down. I tell you where to stop, right? Stop. And now I'm pointing right at it. Okay, this is called the azimuthal angle, but it's the angle I'm making from the z-axis to my point. So there's 3 points. We call this usually phi, or phi, or pho, or phum, however you want to write it. And so here what we say is, I have given you 3 things, and I can tell you a point on a sphere. I can tell you 3 things. 1, I tell you how far away I am. 2, I tell you in what polar angle am I in, kind of where do I need to face in a horizontal way. And then 3, I tell you when I need to face in a vertical way. How far away am I this angle? So I start up here as phi being 0, and I move down. Now, what are the angles for all of these, right? How far can these go? Firstly, rho has to be positive. It has to be. And specifically, we can find very quickly by using a nice Pythagorean theorem argument that x squared plus y squared plus z squared is equal to rho squared. In the same exact way that we had over in the polar coordinates section, we had x squared plus y squared equals r squared. Now, the next thing I need to think about is what theta is. Theta is just the polar angle. It works exactly the same, and we calculate it the same exact way by projecting the surface onto the xy plane. So what we usually do is we say, okay, well, you know, theta has to be between 0 and 2 pi. And now what I want to think about is, what is this phi doing? Right, where's phi between? I don't think it's obvious off the top of the head, but let's think about it. So phi being 0 is up here. If I go to horizontal, I have now gone 90 degrees. Okay, I've gone 90 degrees. So that, now I'm at pi over 2. I then go down more, and now I'm at specifically, I'm at the negative z-axis. I'm at this negative z-axis here. Okay, I'm down here now. So I went up to, you know, phi being 0, phi being pi over 2, phi being pi. Does it make sense to go farther back? Or am I done? And the reason is, well, think about it. If I go back like this, it really doesn't make sense, because I could just change my polar angle to face this way and make phi be something different. This between 0 and pi. And so because of this, we can then say specifically that phi has to be between 0 and pi. And so these are your bounds usually for a full sphere. Okay, if I have a full sphere, I have my full 2 pi of a theta. I have a full pi for a full sphere. I don't go any farther than pi for my phi. And what we can do as well is we have a coordinate transformation very similarly to what we had in polar coordinates. It's a little bit more complicated though. Now, I want you to think about it this way. It's going to be a little bit more complicated, but it comes actually very naturally. The first thing we note is all of them have to have rows there. I always go row, row, row. That's how I remember it. Now, the polar angle is the same as this angle over here. It's the same thing. So if I was to have a coordinate shift, you would think that I probably should have cosine b with x and sine b with y, and you'd be correct. So I still have cosine of theta with this and sine of theta with this. Now, how do I think about what the phi direction is going to be based off of? Well, if I come back up here really quickly, and I project this onto this xz plane, which is actually a very, very common technique that we will use, we actually will get this angle as phi. Okay. Now, I hope you'd agree, if I do this, I actually gain this triangle, this phi, and this right here is phi as well. And now what's interesting here is this x component. If I want to find what this is, well, if we're doing SOHCAHTOA, right, if I'm doing SOHCAHTOA here, I would need that this phi, it's an opposite to this side. if I'm thinking about an x, right? This is the x, and this would be that. So it's opposite to that side. So would be so control. So I need a sine. And this is what happens. If I do the same exact thing, projecting it onto the YZ planes, I would get the same exact thing. So because of that, we then have a sine of phi in both of these. And because of my z component is here now on this projection. We see that it's going to be adjacent to phi. And so therefore, I'm going to have a cosine related to that. And these are your coordinate transformations. So how I always remember it, I have 3 rows, row, row, row. I need that. Cosine and sine, always need that, right? As a similar to polar, that doesn't change. And then what I usually do is I remind myself that y, I usually remind myself of y, it has to have the same sign. It has to be sine, sine. Which then means x has to have a sign, and then z has to be different. You're going to remember it based off of this too, thinking about the projection and thinking that it's going to be the opposite here. In that case. And that's why, mainly, this is what we're going to be doing a lot of times when we come up with bounds of integration for these things. The last thing we need to do is think about what the integral is going to be, the shift. Here, if you recall, if I was to do cylindrical coordinates, if I change this dv here in my cylindrical coordinates, what I would do is I would do an r dz dr d theta. Right? I would have to add this differential r. Now, why would I do that? Because again, we need to match up dimensions in a way, right? So I have a length to the third. If I just had this, I have a length squared, and this doesn't have any dimensions because it's an angle. So I have to make it that r. That way. Now over here, it's a little bit more different. So let me just kind of remind ourselves. Let's write this down a little bit more formally. I move this over here now for our spherical coordinates. If I now want to create my dv here, I'm going to do d rho, d theta, and d phi. I'm going to do all 3 of these. Now, I need dimensions to match. This is an L to the third. Right here, I have a length. This is not a length, and this is not a length. Nothing. So I need a length squared on this side to keep the dimensions the same. And in order to do that, what I do is I make this L squared. So I need to make this a rho squared because it's the only length scale I have. So I add a rho squared to my list here. The last thing we do need, and this is because of this kind of coordinate shift that happens here, because of this sign aspect, we try to think about a volume. What does a spherical volume look like, a spherical wedge volume? We actually need to include a little bit more of the phi component to kind of counteract this whole thing, to make the volume equal. So we add this sine of phi. If you're wondering where this fully comes from, this sine of phi part, it actually comes from this thing called the Jacobian of a matrix. The Jacobian of a matrix. The Jacobian matrix, the determinant of that, which actually tells us how to switch from Cartesian to another coordinate system. And it tells us what we need to flip this. And here it will tell us that we need rho squared sine phi. Okay, so with this now in mind, let's think about some problems. How do we do these kinds of things? I think the first thing, and a very, very basic thing, is to try to do here, is to try to calculate the volume of a ball of radius, let's say 3, okay? So if I tell you this, right? So if I want to calculate the volume of the ball, x squared plus y squared plus z squared, let's say less than or equal to 4. Okay, so a ball of radius 2. I want to calculate that volume. As a reminder, what the volume is, right? It's a triple integral E dv here. So that's just a 1 in the integral. And if I do this here, we actually know this formula, right? It's 4/3 pi r cubed, right? So we can actually do this off the bat, right? It's 4/3, right? 4/3 pi r to the third. In this case, it'll be 4/3 pi, 2 to the third, which is equal to 32/3 pi. So I get something like that. I don't even need to know the integral, but let's try to prove via the integral that this is actually the answer. So the first thing we want to think about is if I have a full ball, and I'm going to draw this out very, very rigorously, just to show you the process of what one would do. I'm actually going to get something. Hold on. It'll be a lot easier to think about. I have actually a sphere. A sphere right here. So I'm going to draw this sphere. It's going to be a bad sphere. Just be aware of that. Because it's very tough to draw a sphere here. As much as that is. Kind of like this. Okay, I have this ball. All right. Now, my rho here. How do I come up with that? Right, I need to figure out all my bounds. My rho, my theta, and my phi. The process is as follows. What we do, yeah, I can write it this way. So what we do here for rho, we start off at 0. We start off at the origin, okay? I hope you'd agree that the origin is inside my ball. So therefore, because of that, we start off there. I know I'm going to be starting at 0, okay, if it's inside my region. And then we go out of the region, directly out of the region in different ways, as many ways as possible. And if you notice, I'm always leaving from the edge of the ball. I'm leaving the edge of the ball, which is equal to x squared plus y squared plus z squared is less than or equal to 4. And now what's interesting here is to remind ourselves that we do have this coordinate shift, x squared plus y squared plus z squared is equal to rho squared. So realistically, we could actually write this. It would go rho squared is less than or equal to 4, or mainly rho is less than or equal to 2. Because rho can't be negative. It's an important thing to remember. Rho can't be negative, r can't be negative. And so therefore, rho will go from 0 to 2. Okay? And so that's what I do. Usually the rho is usually the easiest, honestly, out of most of these. Sometimes it get a little bit complicated, but if we have a spherical wedge, this is really, really simple. The next thing to think about is this theta component. Okay, for theta here, the process is we project onto the xy plane. And why do we do this? Because it's the polar angle. And I hope you'd agree if I project this surface onto the xy plane, that's the same thing as actually putting a z equal to 0 here, right? I kind of just project that down. Or I just take a look at it from the top. And I hope you agree, we're looking at it from the top on the xy, it is just a circle. Right? It's just a circle. If I look at a ball from the top, it's going to be a circle. If I look at a ball from any side, really, it's going to be a circle, right? But at least here, I know I'm looking at it from the top, it's going to be a circle. And so I project that down, and that's what it's going to be. I don't care about the radius of this circle. I don't care. I don't. All I care about is coming up with the theta component. That's it. And I know I have a full circle, so I know I'm going to be between 0 and 2 pi. That's where I get that. And lastly here, what I want to do is come up with this phi component. Now, the phi component usually is the difficult one for most people because it's a weird angle that we really haven't tackled before. But again, it's the angle that we see, again, pretty important. It's the angle that we have from the z. And what we did here, as I hope you saw, is we projected this onto the xz plane. Okay? So what we do here, we either project onto, we're going to project onto either the xz or yz planes. It is okay to do either. You're going to get probably the same exact answer both. You're not going to probably, you will get the same exact answer both times, unless it's a very, very, very special case, which is not going to happen. So let's do xz plane. I like to think about it. So again, I'm going to project on the xz plane. I'm just smushing this guy, right? Like this way. Okay, that's what I'm doing. I'm just smushing it. It's again going to be a circle. This is again a really, really easy example, but I just want to kind of show you the process that we use. And now what we do, and as a reminder, let me show you what this is. Phi equal to 0 is on top. You are allowed to go counterclockwise or clockwise, whichever one you would like. Whichever one is the way of where your phi, where your projection is. If it's symmetric on both sides, it does not matter. You can go either way, which is really nice. If it's one side than the other, it's okay. Just go on that one side. We usually then, I'm going to go in the clockwise direction. I like to think about it that way a little bit more, but you can do either. So if I go down in this direction, like this right here is phi over 2. If phi equals pi over 2, and this one is phi equal to pi, all the way down. And so if you see here, we go from all the way up to all the way down. And again, you might be thinking, what about the other side? We have already got that covered by the theta. I don't need to worry about it. And so therefore, we get that I'm between phi equal to 0, we always start off there, and we go all the way down, and I get phi equal to pi, okay? So I go from 0 to pi. And these are the bounds. And just as a reminder, if I have a full phi from 0 to pi and a full theta from 0 to 2 pi, I must have a full circle. Guaranteed. Full sphere. Must have a full sphere. If I don't have a full sphere, I cannot use these bounds. I have to come up with something else. Okay? So, with this in mind, as you can see here, this is a rectangular domain because it's all constants, because a sphere, it's a spherical rectangle in some way, right? And so what we can do is now I evaluate this volume integral by switching coordinate systems. And this becomes now the triple integral from 0 to 2, 0 to pi, 0 to 2 pi, of rho squared sine phi. We always need to add this in there. Rho squared sine phi. And then I'll go d rho, d theta, d phi. Usually this is the order we usually go in. It doesn't really matter unless one of these is dependent on the other, then it does matter. Usually you go rho, then theta, then phi. And now what's really nice here is because I have a separable function. I'm sorry, I've written this actually incorrectly. The 2 pi should be in the middle. Sorry about that. Right, from 0 to 2 pi. So since this is a separable function and these are all constants, we can utilize Fubini's theorem. Not even Fubini's theorem. I mean, we could if we wanted to, but I can use the fact that they're separable to integrate each one individually. So the phi comes along. I have the sine of phi d phi. I then have the integral from 0 to 2 pi of d theta. And I have the integral from 0 to 2 of rho squared d rho. Something like that. The integral of sine is negative cosine. And we're between 0 and pi. This is going to be just 2 pi. And this is going to be rho to the third over 3 between 0 and 2. Here we see that we're going to have negative cosine of pi, which is going to be 1, minus negative 1, which is going to be 2. Doing this, we're going to get 2 here. We'll get 2 pi. And then we'll get 8/3. Because I would just plug in the 2 here, I'll get 8/3 here. And if I plug these in, I get a whopping 32 pi over 3, which is our answer that we got up there. Seems like a thing. And this is actually where the formula comes from. If I go ahead and do this, so I just left this with a regular r. I just left this with a regular r here. You can actually see that I would actually just get 4 pi over 3, and I would get r squared, r to the third. That's the formula, and that's where this comes from, which is nice. So that's how you kind of do these problems. Now, this is clearly a pretty trivial problem because I have a full ball, but you know, we didn't have to convert it all. But this is actually a really interesting way of going about it and thinking about these different things. So let me kind of do this here, kind of show you maybe a little bit more of a process, maybe to do one of these. So if I go ahead and do this now, I'm now going to find I have a problem here. Boop, 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 boop. Yes, great. So I have the problem. I'm going to try to evaluate or just exchange here, because I think it's actually a very, very long problem, and I'm not going to do it all. dv, I want to evaluate this integral where e is the portion of the ball x squared plus y squared plus z squared less than or equal to 1 in the first octant. Okay? So I'm in my ball of radius 1, and I'm only in the first octant. And I want to convert this to spherical coordinates. I'm not going to go through the whole problem because these start to get really, really long. And so the technique starts to get a little bit crazy. But I'm going to start to try to convert this to a spherical coordinate problem, maybe just evaluate it. Now, why would we go about trying to do spherical coordinates, right? I'm going to first off draw this region. Z. Well, first off, we're on a sphere. Maybe spherical coordinates would be helpful. There's also another hint. Here, if you notice, if I convert this exponent, x squared plus y squared plus z squared, I would convert this to rho squared, which is pretty nice. If you think about it, it's not too bad. So in this case, I'm just with a ball of radius 1 just in the first octant. So I'm here. Just this guy. Okay? Just that guy. Now, if I'm in the first octant here, that's coming into play, I want to first off figure out my rho. If I'm going to do this to spherical coordinates, because I see I'm on a sphere, I might as well. Rho here, what I'm going to do, I start off at 0. Right? I enter here. I see 0 is in my domain because I'm inside radius 1 and I'm in the first octant, so my rho is going to be from 0. And I'm always leaving. And again, you could see that from rho squared less than or equal to 1, and we get rho less than or equal to 1. So I know that rho has to be bounded by 1. Theta, what I do for theta now is always project onto the xy plane. What does this look like when I project down? Well, I hope you'd agree, it's just this quarter circle here. So if I project this onto the xy plane, it's going to look like this quarter circle. Again, I do not care about the radius. It's the radius of 1, sure, but I don't care. All I care about is what it looks like. And it looks like a quarter circle, because it is. And I now want to just figure out the theta bounds for this, which is just as regular, just from I have theta being 0 here, I go all the way to theta being 2 pi. Sorry, pi over 2, right, on this guy. So that's where we get that. And lastly, here for phi. Let's project this onto the, let's do this, I think it's a little bit easier maybe onto the YZ plane. So imagine smushing this onto the YZ plane. Just, ha, it's like that. If I flatten it out, I hope you'd agree on the YZ plane, it would look very similar. It would do that guy. Right? It would be like that. And again here, what I do is I say that phi equals 0 is here, and I know, now note, I can go either way, but the only way that I can go, because this is the region I need to go in, I need to go in the clockwise direction. And so here, what I'm going to do is I'm going to go from phi equals 0, I'm going to go down to phi equals pi over 2. So because of that, if I'm above the xy plane, I'm going to be from 0 to pi over 2 kind of thing. And so from here, what I get is it becomes 0 to pi over 2. And so these are my bounds for this integral. A couple things I'll need to do to kind of really change everything too. This x needs to change. This integrand needs to change to spherical coordinates. Remember, my x bounds as a rho cosine of theta sine phi. This will change it to a rho squared. And I have to remember I have to do my rho squared times sine of phi. So let's do all of that here, over here, which will now become 0 to 1, 0 to pi over 2, 0 to pi over 2. I would then get the x here is a rho times cosine of theta, sine of phi. I would then get e to the rho squared, because this could be exchanged for a rho squared. And then I would get here I would multiply this by a rho squared sine of phi, because that is my change in variables. This is d rho, d theta, d phi. Phew. Okay, this is really long. I'm not going to go through this anymore. I just want to clean this up. But to kind of show you here, you can now split this up into 3 integrals, because these are all multiplied together. And I can just separate them all out. So the first one's the rho. I have a rho to the 3rd e to the rho squared from 0 to 1. Rho to the 3rd e to the rho squared d rho. I would then have a 0 to pi over 2 of, I'm going to use my theta here. My theta here is just cosine. And lastly here, I would get a sine squared of phi from 0 to pi over 2. And I will stop here. But this is not too bad to integrate. This one you would utilize a double angle formula, like 1 minus cosine 2 theta over 2. And over here, this is actually kind of a u sub plus an integration by parts. I think the u sub here you should probably use is equal to rho squared. And remind yourself that you can write rho to the 3rd as rho times rho squared. And then from there, actually use integration by parts again. So it's going to be kind of a double integration by parts. But this is at least the process, right? And that's easily the most important part. Integration techniques, sure, they exist, and we can find them and do them. But this is kind of the process. So as a reminder, to find theta, project onto the xy plane. To find phi, project onto the yz or xz planes, whichever one you want. To find rho, you start from the inside, usually it starts at 0. We go to the edge of the circle, the sphere. In this case, if I have concentric spheres, like if I have a sphere within a sphere, kind of like Inception style, or like Russian nesting doll style, then I wouldn't have rho starting at 0, right? I would have something maybe like rho going from 1 to 2 if I have that. Okay, so let's try one more to kind of show you a little bit of a process there. One more process. We're gonna find the volume here. Let me actually pull something up. Something like this. So for spherical coordinates, it can start to get a little bit hairy. I understand. And why would you change things to spherical coordinates? I understand. Sometimes it can be pretty complicated. You know, we can kind of go backwards to here and kind of say, yeah, we're gonna try this one. So let's try the volume. It's actually a good problem. We'll end on this one. The volume, we're gonna go within the sphere of x squared plus y squared plus z squared is equal to 4. So inside that sphere, you can't see the problem at the moment. You should yell at me. Within the sphere, above the xy plane, and below the cone, z equals the square root of x squared plus y squared. Okay, there's a lot here. And this is kind of complicated. So as much as we can, let's try to draw this out as picture as best as we can. Let's try it out. So the first thing I want to note, if I could draw my z, is we're above the xy plane. I don't have to worry about anything below it. And so I'm within my sphere and below the cone. I am below the cone, which is a little bit complicated. But I find this to be a really good problem to think about a lot of things, especially phi here. First thing I'm going to do is draw the sphere. The sphere is pretty not bad to draw. Kind of like that here. And I'm going to go around like that. Yep, something like this. Something like that here. So I have this sphere. Okay, so I have this sphere. And then I'm within this sphere. So I'm inside of it, and I'm below the cone. So let me draw a cone with blue here. Below this cone. So like the cone kind of comes up like here and intersects. So I am below this cone. So I have this ice cream cone, and I'm below it. So more specifically, I'm down here. Yeah? So I'm down here. So it's kind of like a circus tent in a way. Like I have this middle part and it's kind of all going over, and I'm trying to find the outside. So it's outside the cone and inside the sphere. And so this is my region of integration. Now, this starts to get really complicated. Like, how do I go about this, right? But just remind yourself, again, and this is a really important thing to remind yourself, is always ground yourself in what you know. It's the same process every single time. Rho, theta, and phi. Now think about why this is gonna be really nice to think about rho, theta, and phi here, right? You might not think about this initially. You might go, why can't I use cylindrical coordinates? You can. It might just be a little bit more complicated here because I would have to project things onto the XY plane and actually worry about what radii look like. You know, it could start to get really complicated pretty fast. And so because of that, you know, spherical coordinates, I'm on a sphere. So let's think about if my spherical coordinates start getting bad, sure. I mean, we could definitely go cylindrical. But let's think about it this way. The first thing I'm going to do is I'm going to think about rho. In rho here, I'm going to use a yellow marker. I start here. And how do I exit the region? Right? I start here, and I always exit like this. Right? Something like that. So what's happening here? I'm entering the region at rho is equal to 0. Rho is equal to 0 is in my region. It's there. So I start at 0. And I'm always exiting. I'm never exiting from a cone, right? I have to go into my region and out. Even if I'm up here, right, I'm always just getting closer to this. I'm getting close to the cone, but I'm not in the cone. And so therefore, I'm exiting through the sphere. The sphere here is rho squared equal to 4, which is rho equal to 2. And so my rho is between 0 and 2. Great. Again, what do we now do to find my, in this case, what do I do to find my theta? I project onto the xy plane. If I look down on this, would you agree I would just get a circle? It would just be this circle. I would see that circle, right? I would see that full circle. That's what I would see. And you can't see that, but that's what I would see. I would see this full circle, right? Because it's all the way around and it's that full circle. So my theta goes everywhere. I need to get all directions. I need to get all sweeps. And so therefore, this is going to be between 0 and 2 pi. Not too bad. Lastly, phi. What happens there? Phi again is now going to be projecting it onto the xz or yz planes. I think here it's always a little bit visually better to think about the yz because how I've drawn it. So let's do that. If I project this onto the yz plane, imagine flattening this, as pushing it against there. Would you agree? I'm going to do the yz plane. I'm going to look something like this, right? It's going to look like this, and it's going to come down like that. It's going to be this region here, right? Because I have this cone, I have this dead area in this cone, this part, and then I have this part that's in my region. Yeah, something like that. Now, from here, I note a couple things. The first thing is that phi equal to 0 is on top. I probably should do this in a different color. Phi equal to 0 is on top. And phi equal to pi over 2 is on the bottom. And I don't start here. I don't start from phi equal to 0 anymore. Where do I start? Well, I have to go in this direction. It's on both sides, right? I'm sorry, if I project this, it's on both sides, right? It's actually kind of butterflying. Right, because I kind of think about this. I project this, I'm actually going to get both parts here, which is okay. As you can see, we can kind of go either direction because it's going to be symmetrical. So I'm going to go ahead in that same direction here and kind of still go in this way because it still covers the other side because of our theta. Our theta covers the other side, so we're okay. I go in this direction. I kind of sweep in this direction, and I end up at this line. And what's this line at? What is this line? Well, this line is the cone's line, which is a right cone, and so therefore, this is the line y equal to x. Because of that, in this case, it's y equal to z. But here, what's going to happen is this is going to actually be by pi over 4. It's going to be a 45-degree angle. And so if you notice here, my phi here is going to be between pi over 4 and pi over 2. This other side is covered by my theta because I go and sweep in the other direction, right? It would be going in this direction, right? Thinking about that. And so therefore, these are my bounds. And therefore, my integral for my volume becomes 0 to 2, 0 to 2 pi, pi over 4 to pi over 2 of, now I have to make sure I add a rho squared sine of phi every time, d rho, d theta, d phi. And we could integrate that if we wanted to. It's not too bad. We get something like 8/3, maybe, yeah, 8/3 times like 1 minus 2 square root of 2, something like that. Yeah, something along the lines of that. So we would get something like that. And so this is my integral, which is not too bad to integrate then. Spherical coordinates is probably going to be the best here. You could use cylindrical coordinates by noting that maybe I always enter the region. It's actually tough to do cylindrical. I'm actually realizing it's very tough to do cylindrical coordinates because if I go do z here, I'm entering and exiting from 2 different points, right? I would sometimes exit from the cone or I would exit from the sphere, which is different, which is very difficult. So spherical coordinates is really the only way you can go about this. So this is the process. project onto the xz plane and yz plane for phi. Start at your z-axis and go from there. So that's kind of the idea of cylindrical coordinates, spherical coordinates here. They're very helpful, honestly, and they have a lot of really, really good, interesting properties. A couple things to remember. These coordinate shifts are really important to remember. You know, the big one here is to remind ourselves that if I say x squared plus y squared plus z squared, to get rho squared. These are pretty rare, but they're just good to know, especially if you have to convert to something. If you had something like over here, right? If you had something like that, it's important. On top of that, though, you have theta from 0 to 2 pi and theta phi from 0 to pi for a full circle. And projections are your friends here. That's kind of it. If you have any other questions, let me know. I will be starting then, my next videos will probably be either the review sessions, and then on top of that, I'll be doing a little bit more of chapter 16 now, getting into vector calculus and kind of combining everything we've done in the last 3 months, kind of all coming out to this. If you have any questions, let me know. I hope you're doing well, and I'm gonna, please dance. Have a great day, guys.